This is Mr. Mitchell with a video talking a little bit more about this free fall acceleration that we've seen in a previous video. Free fall acceleration is when the force of gravity is the only force that is on a particular object. Here we have a hang glider falling straight down. Here we have a basketball that's apparently falling straight down, apple, safe, tennis ball. Anything that's falling straight down, the only force upon it is gravity if it is just dropped. So that's what free fall acceleration is. Now, Galileo, and you know that you probably talked about Galileo before, but Galileo is famous for having been on top of the Leaning Tower of Pisa and dropping two balls that were of different mass. And those two balls of different mass ended up hitting the ground at the same time. You know, people would expect the heavier ball to go faster through the air than the lighter ball, and that's just not the case. They fall at an equal rate. In fact, everything falls at an equal rate. The only exception is because of air resistance, like a feather would have more air resistance. But any of these objects over here, they fall all at the same rate, and that rate happens to be down at the bottom. It is 9.8 meters per second squared. So I guess the question is, why does every object fall at the same rate? We can figure this out just by looking at the formulas. Here we have an example we had before. We have a little car, we have a big bus. The little car and the big bus, they have different forces, because if they are going at the same acceleration, one of them, the bus, has an incredibly large amount of mass compared to the other. So they would have more force. The larger the object, the more force it has because of its weight. Now, we talked about these with momentum. That kind of falls through with momentum. The one that has the heavier weight, if it is going the same speed, is going to have more momentum, and that's kind of similar to this equation here. But what we're looking for is acceleration downward. Acceleration downward. I know that it'd be probably hard to have this happen, but if you had both of these things falling downward, let's look at what the acceleration downward would mean. We've already kind of established that the bus would have more force than the car just because it weighs more. So if you have something that weighs more accelerating downward, then its force here is going to be a big number. But what else is going to be a big number? This M stands for mass. So the mass is going to be a big number. If you have this small vehicle here, the small vehicle will have a smaller number for the force, but it will also have a smaller number for the mass. Think about this. If you have these two figures, the figure for F and the figure for M, whether they're small or large won't make much difference. If this F is, say, I'm just picking a number out of a hat, 100, and the M is 100, you still have the acceleration of 1, even if this F here were 2 and the M were 2. It doesn't matter how much mass or how much force, they're going to kind of counteract each other. So if this bus were falling, it would have a lot of force, but would also have a lot of mass, and you don't multiply the mass times the force. The mass makes it more resistant to fall than it does this car. This car has some mass that makes it resistant to fall, but it equals out, you might say, with the force. So the bigger the object and the smaller the object doesn't make much difference as far as acceleration, and it seems that it makes no difference whatsoever, because the acceleration for all falling objects is 9.8 meters per second squared. Same thing for the big bus, same thing for the little car. Now, let's talk about objects falling. we have a chart here. I think it was actually a NASA website where I got this from. But every time you have something falling, here we have two spheres that are falling, presumably from the Galileo experiment. This particular one, both of them, the first second, it didn't fall 9.8 meters. And that's kind of a misnomer whenever you hear 9.8 meters per second. People think, oh, it fell 9.8 meters. And you know, I think I might have told you incorrectly in a previous video, just kind of talking casually. But it didn't fall 9.8 seconds the first second. It fell 4.9 meters, I should say. It fell 4.9 meters the first second. After the second is complete, it had fallen total 19.6 meters. So notice the second, it fell, what is that, 14 point something meters. And then the third second, by the end of that, it had fallen 44 meters. It is accelerating. These objects that fall are accelerating. Now, where do we get the 9.8 from? It's the speed, the velocity in between each second. From 0 to 1 second, its speed, or velocity, is 9.8. Subtract what happens from the first second to the second. 19.6 is its speed the second time. Subtract 9.8 from it, that makes it 9.8. Look what happens in the next second. Every single second, it is accelerating 9.8 meters per second. It's accelerating 9.8 more meters per second every single time. So what you have, this is what the constant is. The acceleration is 9.8 every single one of these, but that doesn't mean it's going to fall 9.8 meters, 9.8 meters, 9.8 meters, 9.8 meters, 9.8 meters. It's going to accelerate. And if you have something small like a penny that was dropped from the top of the Empire State Building, there's no telling how much acceleration it would have by the time it hits the ground. But in the real world, we do not have a vacuum in our atmosphere. In a vacuum, you do not have the one force that counteracts gravity somewhat. It is air resistance. As this guy here is falling, he's going to fall at these rates up here at 9.8 meters per second square, and he will accelerate the more seconds he is in the air. But what's going to happen at some point, the air resistance that is pushing up against him will equal the force of gravity that is coming down. Now remember, air resistance increases with surface area and speed. So at one point, this guy will be going fast enough to where the air resistance will keep him from accelerating anymore. And that velocity is called terminal velocity. The terminal velocity is that point where the air resistance prevents anything falling from accelerating. I'm trying to think, I saw some figures in studying for this, that terminal velocity is met after about 12 seconds of a person falling. Now that would be different with something like a penny, because a penny doesn't have near the surface area that this person does. So the terminal velocity would be different depending on the surface area of what's falling, because the speed will be pretty constant. Let's see what's coming up next. Oh yeah, let's talk about weightlessness. Now, here we have some people standing right at the very top of a big mountain. Now, we have mentioned before that the higher you go in altitude, the lower the value of G. Whenever you're at sea level, the value of G, of course, is 9.8 meters per second squared, but the farther up you go, the less G is. So, when you get so far up you are in outer space like this woman is, Do you just not have any G? Do you not have any gravitational force? Of course you still have gravitational force. But why is this person not standing upright? Why does this person appear to be floating? And the key word there is appear, because she is not weightless. It is what you call apparent weightlessness. Now I can kind of explain this hopefully with this diagram. Oh, the reason she's going very fast is because of her speed. Let me explain. Let's say you have the Earth, and somewhere on the Earth you have a cannonball inside a cannon. When you shoot this cannon, it will travel a long way. The cannonball will. It will travel a long way, but after 4.9 after 1 second, it will drop 4.9 meters, just like everything else, which means that it will have already hit the ground before that second was up. But what if you put more gunpowder in this cannon? You can have the cannon shoot farther, but still after a certain amount of time it will fall. But conceivably, can't you keep increasing the gunpowder and keep increasing the gunpowder and make it shoot even farther, where it's going even faster, and eventually it will fall to earth? If you could shoot that cannonball, if you could shoot that cannonball fast enough to where the earth below it has moved. You know, the earth is going at a pretty fast pace in outer space. Now, we can't shoot a cannonball that fast, but what happens is, if you can shoot a cannonball that fast, it eventually will fall, but when it falls, the earth will have moved out from underneath it. And that's what happens whenever things go into orbit. They are just going so fast. Whenever this person right here was shot up into space, they were in a rocket ship that was going so fast that the Earth moved underneath it before it could fall to Earth. And yes, we know what that speed is. That speed is 8,000 meters per second. Think of 1 second. Boom, boom. That was 1 second. If you can have something travel 8,000 meters in that boom, boom, 1 second, you can get something into orbit. And that's something you're going to have massive rocket engines just to be able to do. So hopefully that explains a little bit about the weightlessness, or the apparent weightlessness, because this lady right here is falling, but it doesn't look like she's falling because all the equipment around her is falling too, because it's all going at the same rate of speed. It's all going at the same rate of speed. You don't have a frame of reference. Okay, let's take a look at gravity and the animals. You might not have ever thought about this, but think about all the large animals you have here on Earth. All these large animals have skeletal systems. Even some of the large animals have like exoskeleton systems, like big lobsters and stuff like that. But they have some kind of support structure because of gravity. Their body needs that support. Notice what happens when you have some of these sea animals, like a pufferfish or a jellyfish. They don't have that endoskeleton or exoskeleton like we have. Some sea creatures do. You know, this pufferfish may have some of it. But they're able to exist in the ocean because the buoyancy of the water, there is a little resistance in the water to gravity. You kind of float around, kind of float around. And what happens to a jellyfish when it ends up on land? It sinks to the ground and it can't really move much. And that's because animals in the ocean, you have more larger animals in the ocean without skeletons, just because they can manage the the lack of gravity. It's not lack of gravity, but it's the fact that you have the buoyancy around it, making the effects of gravity not quite the same as it is on land. Well, I hope you've learned a little bit about free fall acceleration.